Greetings everyone and welcome back to our online lecture series for CHE 8030 and CHE 4010. First I want to thank you all for being patient with me and starting to get these lecture videos uploaded online. Hopefully by doing a number of these online lecture videos outside of our normal lecture time, we'll be able to make up for the lectures that we have missed in recent weeks. So where I want to pick up is our example problem of an irreversible reaction occurring in a stagnant liquid film. In this particular problem, again, our liquid film was challenged with a constant concentration of A at the boundary y equals 0, and the liquid film was sitting on top of an inert solid, and what we had was the molecule A diffusing into the film. Inside this liquid film, it would then irreversibly react to form our product B. So we wrote the original differential equation for that. Then we defined dimensionless variables, specifically eta and theta, for our length and concentration respectively. And then we also ended up defining a Dom-Kohler number, and at some point we also defined this lambda term, which we really didn't talk about at the time, but I do want to point out that lambda here has units of length, and what you'll see here in a second is that that lambda essentially represents our reaction zone for our problem, because that's a big part of some of the early stuff that we do in this course is understanding where we have dynamically interesting things occurring in our system. And so for this particular problem, we are going to be talking about a dynamically interesting length scale. And then in further lectures, we will start working on problems or work through problems related to dynamically interesting time scales. Okay. So after defining our dimensionless variables, and quickly I'm going to interject here, I'm going to work through or talk about this relatively quick because we have gone over this in previous lectures. So defined our dimensionless variables. From those dimensionless variables, we were able to recast our governing equation as well as recast our boundary conditions for the problem, where again our boundary conditions were no flux at that inert solid and then a constant concentration at y equals L, or in this case when eta equals 1. And so the first scenario we talked about was when we had slow reaction kinetics, i.e. when the Dom-Kohler number is much less than 1. Based on our differential equation, let me switch colors. When the Dom-Kohler number over here is much, much less than 1, that second derivative with respect to eta is much, much less than 1. And so using our definition of the second derivative in terms of in terms of an order of magnitude analysis, the first thing that we can state is that this delta eta cannot exceed a value of 1. Y goes from 0 to L, and so there is no way that any delta eta can do anything but exist between that range of 0 to 1. So it cannot exceed a value of 1. So for this particular inequality to be true, we know that the delta theta must be much, much less than 1, with delta eta being equal to 1. And so physically what that is saying is that I have a reaction that occurs over the entire film thickness. Therefore, we can feel confident that we have scaled our problem properly by using L as the variable by which we have scaled our coordinate y. So that's the case for slow reaction. The next thing we looked at was the case for when our reaction kinetics and our diffusion kinetics we're on similar orders, i.e. the Dom-Kohler number is on the order of 1. Looking back at our equation, if the Dom-Kohler number is on the order of 1, we know that our second derivative here is on the order of 1. Again, implication here is that theta is on the order of 1. We definitely know that theta is on the order of 1 based on how we have scaled it. So, second derivative with respect to eta on the order of 1. We can infer from that that our delta theta is on the order of 1, with delta eta being equal to 1. So again, what we're saying physically is that we have this reaction of reactant A being converted to product B, and that reaction is occurring over the entire thickness of the film. So we feel comfortable with that length scale being the thickness of the film that we're choosing to scale our Y variable. The more interesting case occurs when we have fast reaction kinetics, i.e. the Dom-Kohler number is much, much greater than 1. So, looking back at our differential equation, if the Dom-Kohler number here is much, much greater than 1, that implies that the second derivative with respect to eta is much, much greater than 1. Based on how we have scaled our problem, we know that delta theta cannot exceed a value of 1. Therefore, the only way for this inequality to be true is if my delta theta is on the order of 1, with my delta eta being much, much less than 1. So physically, what am I saying? Well, first, mathematically, what I'm saying is that I have improperly scaled that variable for this particular scenario. I can do better. Physically, what I'm saying, and we talked about this before, is that what I really have is and I'll draw it as a solid line, I have this very thin thickness, or small thickness, that we will define as delta for right now, within the top of my film, so starting at y equals L, some depth into that film of delta, all of my reactant A is entirely consumed and produce reactant B. Wow, let me see if I can say my kinetics properly here. There is a depth, delta, into the film, after which all of your reactant A has been consumed and has been turned into product B. Therefore, after delta, right, so any point after delta, the concentration of A is 0. And so it serves me no purpose to turn around and model my problem as if I now have this finite boundary out here as my inert solid, when in fact, for the majority of this 0 to L thickness, I have no concentration of A. And so the first thing we're going to do is we're going to use an order of magnitude analysis to determine what that scale of delta is, right? Get an estimate of what that number is. And we're going to do so without ever solving the differential equation. And then the second thing we're going to do is we are going to rescale the differential equation and come up with an analytical solution to that. And in doing so, also prove to ourselves, right, what the general order of that delta term is. Okay. So, let's do the first thing what did I say? I said we were going to do order of magnitude analysis. Okay, so let's just look at the difference. Wow, let me start over. Let's just look at the differential equation. Second order derivative of theta with respect to eta is equal to the Dom-Kohler number times theta. Okay, so first important thing that pops up here. If we have an equation, and that equation contains just two terms, neither one of those terms can be neglected compared with the other. Right? They can both be 0. Right? This could be 0 equals 0. That's the arbitrary solution. But when we have an equation that has two terms, we can't neglect either one of them. Right? Therefore, these terms need to balance themselves. So let me recast this as delta theta delta eta squared is on the order of my Dom-Kohler number times theta. Hopefully we all agree that that term of delta theta is on the order of 1. Theta itself is on the order of 1. And therefore, 1 over eta squared, 1 over delta eta squared is on the order of the Dom-Kohler number, or written in a different way, right? Delta eta is on the order of the Dom-Kohler number to the negative 1/2. Right? It may not be obvious, but if we recognize, if I can spell correctly, if we recognize that delta eta is the same as delta divided by L, then we see that we get the same result or reach the same conclusion that we did from our original analytical solution. What do I mean by that? Well, let's move back up here. Again, we're going to recall that relationship there. And what I just told you in terms of what we originally defined was that the Dom-Kohler number was on the order of L divided by lambda squared, or if we take the negative square root of that, the Dom-Kohler number to the negative 1. Let me write that correctly. The Dom-Kohler number to the negative 1/2 is on the order of lambda L. And I alluded initially that this lambda term has units of length. Essentially what I'm saying here is that my Dom-Kohler number to the negative 1/2 is on the order of that delta, that depth into which I have some concentration of A, and after which all of my A has been consumed, divided by the thickness of the film. Right? So I can establish a relationship between, that's not a good color, let's pick a blue. Right? I have now established a relationship between that delta term and my Dom-Kohler term. And I have done nothing in terms of solving my differential equation. Right? So an order of magnitude analysis is a really nice and quick way to get an understanding of how a particular parameter in your problem might look like. And here that particular parameter that we were concerned with was delta. Right? What was the order of delta? Well, if I do a bit of rearranging, I see that delta is the only order of Dom-Kohler number to the negative 1/2 times the thickness of my film. Right? And so that's great. I have an idea of what I'm looking for without even having to solve the problem. So that was approach 1 to determining the thickness of this. In approach 2, really our main goal here is I'm trying to come up with an analytical solution with a newly scaled variable. Let's go back. We'll pick a darker color. Go back to black. Right. The second method that we're going to talk about is an example of coordinate stretching. Okay, so in this particular scenario, what we are seeking is a new coordinate. Here for us, we'll call that coordinate psi. We're seeking a new coordinate such that delta psi is on the order of 1 in that reaction zone or delta thickness into our film. Because that's what we don't have currently. Right? Currently, our length scale of delta eta is much, much less than 1 when we have fast reaction kinetics. So we are going to pick a new variable psi, and we would like to have that variable scaled in such a way that our delta psi is on the order of 1 within that reaction zone. And so we're going to do something called coordinate stretching. What that looks like is the following. I have psi is equal to 1 minus eta, where here 1 minus eta is my delta eta term. Right, so we're some distance into the film. And we are going to stretch that coordinate, or that very small distance, by a large factor. And that large factor for us is going to be our Dom-Kohler number, because again, we are talking about the scenario where the Dom-Kohler number is much, much greater than 1. Another way to think about that is the Dom-Kohler number is approaching infinity. It's getting really, really large. But we have this unknown parameter of A, which is a constant, and it's something that we need to solve for. Okay, by setting, an important thing here too, setting psi equal to 0 at what we're going to call the active boundary, right, the boundary next to that reaction zone, ensures that psi will be on the order of delta psi in our region of interest, i.e. our reaction zone. Okay. So we have now, similar to what we have done before, defined a new variable. Our old equation had etas. We would like to replace those etas with psis. So we follow our same procedure. And our new governing equation looks like this. Dom-Kohler number to the 2a, second derivative of theta with respect to psi. That is equal to the Dom-Kohler number times theta. Ultimately here, the premise of this variable transformation is that we would like to remove terms that are troublesome in our equation. And so for us, that troublesome term is the Dom-Kohler number. Because when the Dom-Kohler number gets really, really big, our scaled length is no longer scaled properly. So we would like to remove these two terms from our differential equation. This a here is some arbitrary constant, so we can set it equal to whatever we would like. If our goal is to remove the Dom-Kohler number from this equation, the only solution to that would be to set a equal to 1/2. When a is equal to 1/2, hopefully we all agree that this term becomes 1. And then we have one Dom-Kohler number here, one Dom-Kohler number there. Those cancel themselves out. And I'm left with the following transformed governing equation of the second order derivative of theta with respect to psi is equal to theta. So now we have a differential equation where we should feel a bit more comfortable of the length scale because we have removed the troublesome parameter from our problem by defining this new variable for our transformed length scale. Now that we have this newly transformed differential equation, much like we did before, right? We transform the differential equation. We also need to transform the boundary conditions. So let's start with what I would call easier one. That is the constant concentration boundary condition. So before, this was the boundary condition at y equals L, or eta equals 1. But when eta equals 1, psi equals 0. Hopefully we can all see that. So for theta, when psi equals 0, my boundary condition is equal to 1. My other no flux boundary condition now looks like d theta d psi. But if I scroll back up to this problem, or the drawing of the problem, again I'm pointing out, or I want to point out, that after this depth of delta, no matter where I sample in my film, I have no concentration of A. Therefore, this boundary here of my original problem at y equals 0 is essentially infinitely far away from where my new boundary is for my problem. Right? My dynamically interesting length scale. Therefore, I have now converted my problem into a semi-infinite problem. And that boundary condition at y equals 0 is now a boundary condition at psi approaching infinity. Right, so hopefully you all see where that came from. We could also, it would also not be incorrect. Right, another way, or another correct boundary condition here would just be to say that theta as psi approaches 0 is 0. Right, we don't have any A, again, past that thickness of delta into our film. Regardless of which one of those boundary conditions you write down, the exact solution to the differential equation is exactly the same, and you end up with a solution of theta as a function of psi is equal to the exponential of negative psi. Okay, so that is the new solution for our newly scaled problem when we have the scenario of fast reaction kinetics, i.e. the Dom-Kohler number is much, much greater than 1. Hopefully that equation looks a bit familiar because that equation is equivalent to the equation that we wrote down for the example problem when we solved the non-rescaled version. And it's equivalent when we examine the limiting behavior of that exact solution. And so if we remember, right, for I don't want to write that. I want to write the solution. So this would be our limiting form of the exact solution. And we saw that theta as a function of eta, right, approached the exponential of negative L over lambda multiplied by 1 minus eta, again as L over lambda approached infinity. Again, I'm going to point out that for us, lambda is delta, and right, our psi term is equal to 1 minus eta Dom-Kohler number to the 1/2, which, if we remember from our manipulation earlier, right, Dom-Kohler number to the positive 1/2 is equal to 1 minus eta L over delta. Hopefully we can all see that those are the exact same solutions. Again, one of those solutions we got by examining the limiting behavior of the exact solution. The other one we got by doing this method of coordinate stretching, whereby we take this very small coordinate, delta eta, and we stretch that by a large factor, which for us was our Dom-Kohler number. We raised it to some unknown constant, plugged that into our equation, ultimately determined that that constant was a to the 1/2. And ultimately ended up with an analytical solution to that differential equation that looked eerily similar to the limiting form of the exact solution that we went over a couple lectures ago. So hopefully that was a good example to give you an idea of how not only we can use order of magnitude analysis to help us determine an important parameter in our problem, the order of an important parameter. In this case, that important parameter for us was delta, or the thickness of that reaction zone. And then what we can do is we can perform something called coordinate stretching, where we define a new variable. Again, here we defined psi as the following. Worked through the problem, right? Eliminated our problematic term from the differential equation, which was our Dom-Kohler number. Ended up now with our newly transformed differential equation. We then transformed our boundary conditions. And then we used those boundary conditions to come up with the exact solution to our transformed equation. So that is going to be it for me for this particular lecture video. And in the next lecture video, we will cover the heated fin example, which should help provide some direction and help with homework problem number 1 on homework 1.